Space isn't cold. It's empty. Forget everything you thought you knew about temperature in space. When scientists say it's minus 270 degrees Celsius outside the ship, they're not lying, they're just trying to explain something we don't have words for. There is no cold or heat as we understand it out there. Only absolute, merciless emptiness, where your body can simultaneously burn and freeze. A paradox? Yes. And it changes everything. Imagine space not as a freezer, but as a perfect thermos. An ideal one. It doesn't let heat escape. That means the biggest threat to an astronaut isn't freezing, it's being boiled alive by their own body heat. Every heartbeat, every breath, every movement generates warmth. And that heat has nowhere to go. No air to carry it away. No convection. Just you, your spacesuit, and energy piling up inside. It's like being sealed in an oven with no chimney. The heat builds. And builds. And builds. Until you start melting from the inside. Sounds like a nightmare. This is vacuum physics. Physics that flips our understanding of temperature on its head. Before we dive into how emptiness tricks our minds about heat and cold, hit subscribe and give this video a like. You won't want to miss the other cosmic paradoxes we explore each week. Trust me, what's coming will change the way you see the world forever. Why space isn't cold. When humanity first dreamed of space, we pictured it as icy and brutally harsh. The vast stretches between stars seemed like an endless Arctic night. Our logic was simple: the farther from warm Earth, the colder it gets. Climb 10 kilometers into the sky, and it drops to minus 50 degrees Celsius. Fly into space, and you reach absolute zero. Writers in the 19th century described space travel as a battle against bitter cold. Heroes wrapped themselves in furs, stoked furnaces, fought ice on their windows. But when the first engineers started doing the math, the numbers didn't add up. It turned out spacecraft don't freeze at all. On the sunlit side, they actually overheat, so much so that metal can melt. For centuries, engineers prepared to fight cold. Instead, they faced a new mission: keeping the crew from boiling alive. The Soviet Sputnik 1 was the first shock. A small metal sphere orbited Earth, its temperature swinging wildly from plus 50 degrees Celsius to minus 30 degrees Celsius. Why? Because one side baked in sunlight while the other froze in shadow. Space doesn't instantly freeze things. It alternately roasts and freezes you, depending on which way you're facing. Now, add a human. A person in a spacesuit isn't just wearing clothes. They're piloting a tiny spaceship. Inside, a living body constantly generates heat, about 100 watts, like a light bulb. During work, it's 3 or 4 times more. Where does this heat go? Nowhere. The vacuum holds onto it. Yuri Gagarin spent 108 minutes in orbit. Long enough for his ship's basic cooling system to handle the job. But as flights got longer, it became clear, active cooling was needed. Radiators. Liquid loops. Ways to dump heat into the void. Apollo astronauts faced a nightmare. To avoid overheating, their spacecraft slowly rotated, like chicken on a spit. This, barbecue mode, spread heat evenly. Without it, one side would hit 120 degrees Celsius while the other plunged to minus 170 degrees Celsius. Metal would warp, seams would split, and the ship could tear itself apart. On Apollo 13, things got worse. The crew crammed into a lunar module designed for 2 people over 2 days. 3 men now had to survive for 4. Electronics ran. People moved. Heat built up. Temperature rose. They stripped off clothes. Sweat poured down. Condensation dripped from cold walls. Some parts were hot, others were icy. They were both freezing and suffocating from heat. Why? Because in space, temperature isn't real, only energy balance is. Temperature is atomic motion. But in space, there are almost no atoms. Between Earth and the Moon, only 5 hydrogen atoms per cubic centimeter. Compare that to Earth's air, 25 billion molecules in the same space. The difference is staggering. In a vacuum, conduction, touch, doesn't work. Convection, air flow, doesn't exist. The only way heat moves is radiation, light, infrared waves. Picture a spacecraft as a lonely island in a black ocean. It glows, radiating heat. If it absorbs more solar energy than it emits, it heats up. If it emits more, it cools down. It all comes down to balance. That's why spacecraft are covered in gold foil. Not for looks. Gold reflects infrared radiation, trapping heat inside and blocking excess sunlight. It turns the whole craft into a perfect thermos, surrounded by vacuum. And the spacesuit? Also a thermos. But inside is a sweating, breathing human. Without cooling, it becomes a sauna in minutes. This nearly killed Alexei Leonov, the first man in open space. His suit stiffened, and he nearly passed out from overheating. The International Space Station, a city balancing on the edge. The International Space Station is a masterpiece of heat management. Every 90 minutes, it cycles from scorching daylight, plus 120 degrees Celsius, to freezing darkness, minus 150 degrees Celsius. Inside, 6 or 7 people live and work, generating heat like powerful heaters. So where does all that heat go? Into giant white radiator panels. Ammonia flows through them, collecting internal heat and radiating it into space as invisible infrared light. If one fails, the station must be evacuated. There have been emergencies. Cooling systems broke down. Crews shut off non-essential gear. Temperatures climbed to 35 degrees Celsius. Astronauts worked drenched in sweat, racing to fix the pumps. 2 days later, when cooling resumed, relief was palpable. The Moon, where day is hell, night is ice. On the Moon, conditions are even harsher. Daytime, 120 degrees Celsius. Nighttime, minus 170 degrees Celsius. A swing of nearly 300 degrees. No atmosphere to soften the blow. Astronauts' suits pumped cold water through tubes to keep them alive. After moonwalks, their suits were soaked with sweat, even though they weren't hot. The Moon gives no mercy. Soviet rovers froze to death at night. Modern Chinese ones hibernate, closing panels, conserving power, waiting for dawn. A future Moon base must be buried underground. Lunar soil insulates well, keeping temperatures stable around minus 30 degrees Celsius. But then, how do you get rid of the heat generated inside? Radiators reaching the surface will be essential. To survive, you must learn to cool yourself, even in the cold. Mars, a planet with a double challenge. Mars has its own rules. Its atmosphere is 100 times thinner than Earth's, almost a vacuum. Days might reach plus 20 degrees Celsius, nights plunge to minus 70 degrees Celsius. Rovers use radioactive heaters to survive. Future astronauts will wear liquid-cooled suits. Movement creates heat. And that heat must be removed. Interestingly, pressure inside the suit must be higher than Mars's atmospheric pressure, otherwise humans couldn't breathe. This creates a balloon effect, the suit becomes rigid, and any movement requires effort. And every effort produces more heat, which needs to be removed. Venus, the planet that was boiled alive. And Venus? That's hell. 470 degrees Celsius. Atmospheric pressure like a kilometer underwater. Sunlight gets in, but heat can't escape. A runaway greenhouse effect. Soviet probes lasted minutes before melting. Electronics fried. Hulls deformed. This is a planet boiled alive by its own atmosphere. And this is a warning. Because Earth is slowly becoming more like Venus. Not as extremely, but the direction is the same. We increase CO2, strengthen the greenhouse effect, and the planet warms. 1 degree in a century represents massive energy, melting glaciers, shifting weather. We're changing the balance ourselves, and watching the consequences. The paradox of life: to stay warm, you must learn to shed heat. Spaceships, suits, stations, they're all fighting heat, not cold. The biggest challenge of spaceflight is learning to radiate heat efficiently into the void. Without radiators, there are no spaceflights. Future ships to Mars will need massive thermal regulation systems. Any failure puts the crew in mortal danger: boil or freeze. The philosophy is simple: life is a fight against chaos. Life can't just exist. It must constantly spend energy to maintain order. In space, this is crystal clear. Every spacecraft is a living system, generating energy, balancing flows. Stop, and it becomes a dead metal tomb. Space isn't romantic. It demands precision, knowledge, attention to detail. And understanding heat is key. Without it, we'd never have left short orbital flights. Spaceflight survives because of physics and engineering, because we learn to control temperature where it doesn't truly exist. The future: thermoses among the stars. Imagine the distant future. Humanity spreads across the solar system. Moon bases mine helium-3. Martian cities slowly terraform the planet. Asteroid stations build new ships. Everywhere, thermal systems hum. Engineers on Earth, Moon, and Mars speak the same language: heat transfer, radiation, radiators, insulation. United by one struggle: the cosmic temperature paradox. Back to the beginning: space isn't cold. It's empty. In that emptiness, there is neither heat nor cold. Only you, your systems, and the unforgiving law of energy conservation. Survival depends entirely on you, your understanding of physics, the reliability of your gear, every decision you make. Space forgives no mistakes. A miscalculation, a broken radiator, and you're in danger. But therein lies the triumph. Spaceflight is a victory of the human mind. We turned vacuum from enemy to tool. We built flying thermoses. Created suits to walk on alien worlds. Built a station where people have lived for over 20 years despite extreme conditions. This is an achievement. A reason to be proud. The temperature paradox once seemed impossible. Now we've mastered it, for orbit, for the Moon, and we're solving it for Mars. But in deep space, on the road to the stars, it will return. Each time, we'll find new ways to overcome it. Earth, our only home. When you look at Earth from orbit, you see it glowing in infrared. A sign of life. Processes generate energy. Life warms the planet. Every crewed spacecraft is a tiny island of warmth drifting through emptiness. An extension of Earth. Our message to space: we are here. We are alive. And we won't stop. Space teaches us not to take anything for granted. Every breath is a gift from the atmosphere. Every warm day results from a fragile balance. Earth is rare. The only planet in our neighborhood where you can live without a suit. When you leave it, you realize how precious it is, and how fiercely we must protect it. Because beyond the atmosphere, there's only emptiness. And a voice that says, if you want to live here, create your own world. Carry your own heat, light, air. Become a planet unto yourself. The icy breath of the vacuum is a metaphor. Vacuum doesn't breathe. But it takes, slowly, relentlessly, if you don't know how to hold your heat. And the sun gives scorching fire without mercy. This duality is the paradox. This is reality. Until we build domes and cities under artificial skies, we will learn, step by step, mission by mission. Learning to manage temperature where it doesn't exist. Because this may be one of the most important skills we'll ever need among the stars.